Hello guys, and welcome to this new video where we're going to practice our CNN skills. So the goal is to build and train a CNN network to distinguish between AI and real faces. So the first thing we're going to do is to import our libraries. Of course, if we're going to need something else, we will do that later on. So we've imported this Kaggle hub that allows us to directly download the dataset, which I'll put in the description, where you need to go and explore it so you better understand this data. So now, after we download the dataset, we're going to train the model. So basically we need to understand the data before we do that. We will look at the directory structure to see how the real and the fake images are organized. So let's do that. We will see that we have the valid test and train roots. The classes are fake and real, which is what we expected. So now we're going to define our image transformation. What we were going to do is resize the images to 64 by 64 pixels, as we did right here. So this parameter would allow us to change the images to make them all 64 by 64 pixels. This is a trade-off because if we use like 32 by 32, it would be faster to train the model, but we may lose some important details. Or maybe if we chose like something bigger, for example 128 by 128, it would be more accurate, but it would be a lot harder and longer to train. So this is a standard starting point. We've also did this to tensor, which would automatically move the image dimensions to be first. So instead of doing height by width by channel, we're going to do channel by height by width, which is what the PyTorch models expect. So next, we will use the PyTorch image folder class to create our main dataset. This is a huge time saver because it automatically finds all the images, assign the correct labels based on the subfolder name, fake for fake and real for the real ones. Oh, let's run this before, and now we do this. We wait a little bit. Okay, so after that we will set up the batch sizes and create the data loaders, because we don't just feed the model all of the instances at once. A data loader would group all of our data into small batches, for example 32 by batches, which is exactly what we did here. So it gets 32 images at a time. This is much more memory efficient and would help us train the model to learn better. So as we said, the batch size is 32. A batch size like that is common and efficient choice. If it's too small, the training can be unstable. If it's too large, it can take too much memory and would train slower. We've also did this shuffle is true. So this is critical for the training loader because it randomizes the order of the images at each epoch, which prevents the model from learning patterns based on the order of the data, and helps it generalize better. So we don't need this for the validation loader. As you can see, we didn't put it here. Okay, so let's run this. This is the output because we printed both of them. Okay, now let's move on. Now we will create a simple function to just grab one batch from the data loader and display it in a grid. This is just like a sanity check. It lets us visually confirm that the data is loaded, transformed, and batched correctly. So yes, we can see a batch from here. It is exactly what we expected. It's 4 by 1, 2, 3, 4, 5, 6, 7, 8. So yeah, we have the correct size. Next, we move on to move the data to the GPU because a CPU can be extremely slower. So I am connected here to the Tesla T4 GPU on Google Colab. So let's do that. Yeah, we are using the CUDA device. Okay. Now we will create a helper function to device and the device loader class. It has small utility that makes basically our life easier. It automatically moves our data batches to the GPU when they're needed, so we don't like move them manually in our training loop. So we do that. Okay, so and now we will define a base class called the image classification base that our main model will inherit from. This class includes training step, which would calculate the loss for one batch of our training data. The validation step calculates the loss and gets the output for one batch. Validation, epoch, and gather all the validation results at the end and calculate the average loss and other metrics. Epoch and is to print a clean formatted log of all results after each epoch. The matrix is a helper function also to calculate the accuracy, precision, recall, F1 score using the scalar matrix. We're going to use a sigmoid bigger than 0.5 to get the final prediction. This is just a programming practice. It separates the training logic from the model architecture itself. It makes our main class, the CNN model, much cleaner and easier to read. So we're basically removing the dirty work. Okay, so here we can see that like we use the binary cross entropy parameter, which is the best loss function for a binary, which is like a yes or no question. It compares the model final probability, which is between 0 and 1, real or fake, to the actual label, 0 for fake and 1 for real, and calculates the loss score. So perfect score would be 0, obviously. We also have the accuracy score parameter for the it's like the simplest metric, correct predictions divided by the total predictions. Recall score, out of all the actual real images, what percentage did the model find? So it's good to know if the model is missing the many real faces. F1 score is the balanced average of both precision and recall. This is often used as the best single number to judge the performance of an unbalanced dataset. So yeah, next we will build the CNN architecture. This is the most important part of the project. So the model will build like several blocks of layers designed to find the patterns in the images. We have this one here where we convolutional layer. It is like the eye of the network. It scans the image with small filters to detect filters like edges, corners, and textures. There is also the batch norm, this one right here, to stabilize and speed up the learning, the leaky ReLU and activation function to introduce nonlinearity, average pool divided by the max pool. This is the to downsample the image to make it smaller, as we've seen in previous video. The nn.linear, the brain after all the features are detected. This is like the final normal neural network that would make the predictions. Dropout, this is just to like a regularization technique to reduce overfitting, where we will randomly turn off some neurons during the training process so it doesn't memorize the training data. Finally, we have the sigmoid. It's our final output layer. So it's right here, where because we have a binary problem, sigmoid squishes the output to be a single number between 0 and 1, which can help us interpret the probability of the image being real. Okay, we can see here like we used 3, 8. These are, as we've seen in the last video, the in channels is 3. Right here, the number of the channels in the input image, it would be 3 because we have an RGB images. 8 out channels, the number of features we want this layer to learn. It would produce like 8 new feature maps, one for horizontal, one for vertical, etc. This is a choice where we will start small and then it will become bigger: 16, 32, 64, 128, 256, and so on. We've picked the kernel size to be 3. This means that the eye, or like the filter, scans a 3 by 3 image, not the image, the pixels. This is very common, and we have padding equals to 1. We add 1 pixel of borders if so we don't shrink the the data. This is also, we've seen it from the previous video. We also have the like average or the max pool method, which is 2 by 2. It would shrink the image like a 2 by 2 kernel, and stride cuts the height and the width in half, reducing the total pixels. This forces the network to summarize information and make it much faster. There we also have the linear fully connected layer. We would expect 256, which corresponds to this or this one. We would after shrinking the image and doing everything, we would pass to the fully collected layer. So we have at the end 256 features left as an input, and we would have 32 out features. So we will be shrinking this down to 32 that the network will use to make the final prediction or decision. And when we say dropout 0.5, we're basically saying that during training we will randomly drop 50% of the neurons passing through this forces the network, as we said, to learn redundant representation and prevent it from relying on any single neuron. Okay, now after understanding this part, did we run the previous one? No, we did not. Okay, let's run this. And next we run this one. Here we will move this model that we named to the GPU. Again, for faster training. These are all like the parameters that we've used and talked about. Now we will go to the training model. We will define a helper function for the training loop. We have the evaluate function, run the model on the entire validation sets and return the metrics. And then we have the get learning rate. It's to get the current learning rate we're using from the optimizer. We will talk more about this later. We have the save checkpoint or the load checkpoint. Also allows us to save our model's progress after each epoch. These are all helper functions that we don't normally see, but as beginners we need them to kinda look at the performance or like the training process. Next we have the fit one cycle. It's right here. This is the main training function. It loops for set numbers of epochs in each epoch. It goes through every batch train loader, calculates the loss, uses the one cycle learning rate, which would gradually increase and then decreases. This is often used for faster and better training. We also have and it also calls the evaluate function to check the performance, logs the results, and save the checkpoint. Okay, so here this is all the code. We see, for example, epoch, which is how many times we loop through the entire dataset, the max learning rate, which is right here. This is like the peak learning rate for our one cycle learning rate function. It's like the speed at which the model learns. We have also the grad clip equals none, which prevents exploding gradients. Like this is a problem where like gradients gets too big, so it becomes unstable during the training. Also have weight decay equals to 0. That's a L2 regularization technique that adds a small penalty to large weights, helping to prevent overfitting. And for the opt function, we will be using AdamW, an advanced and effective optimizer that combines concepts from Adam and weight decays. Also one cycle learning rate, as we said. It's very effective. We start with a low learning rate, gradually go up until we reach the max learning rate, and then starts going back down to almost 0. So we run this. Okay, now we are in the initial model evaluation. What we're doing is evaluate the model on the validation set before any training. We're basically expecting like an accuracy of around 50% because we're randomly guessing here. We didn't train the model yet. It's just like to confirm that so the code that we wrote is working and the model isn't like stuck in one class. So let's do that. Okay, so we can see the accuracy is almost 50% as we said. So moving on, now we are setting up the hyperparameters and starting the training process. So epochs is how many times we loop through the entire dataset. The max learning rate, the peak, as we said. Grad clip is to prevent the exploding gradients. This is a regularization technique, and this one is we use the AdamW, an effective optimizer. So let us set these up and now start training the model. So this would take some time, so we're going to come back when it's finished. Okay, so we just finished the training. It took 46 minutes and 19 seconds. This is with the Tesla T4 GPU, as I previously said. We can see that, as we said, the learning rate starts low, gets high to the ceiling of 0.05, the max learning rate, and then it starts going back down, reaching almost 0. We can also see like the accuracy is increasing, 7.4, here 7.1, but 8.1, 8.7, 8.7, 90, 90 until we reach almost 95%. Also the loss is decreasing and so on. We can better visualize this using charts. So this one to plot the accuracies. We can see that the accuracy is going down as we have more as we use more epochs. Here we will plot the losses. It started going down. Yeah, so this is an important chart for diagnosing a model. Yeah. Here we're plotting the learning rates. This is what we previously said. It goes up until the max learning rate and then starts going down almost 0. Here we defined a predict image function to test our training model using a single image from the validation set. This is like the moment of truth. It's like after adjusting all the parameters, we are making prediction to check if the model actually works on a specific example that we can look at. Here we have, for example, the unsqueeze 0 function or parameter, which because our model was trained on batch of images, to predict a single image we must unsqueeze or add the batch of one dimension. So let me show you an example, because we were trained like this. For example, 32 by 3, 64, 64, and when we introduce a single new image, it would have this vector 64 by 64 with here the like the batch added to a batch dimension is missing, so we would just like add one. This is a very common requirement. Next we have this we need the sigmoid probability to be higher than 0.5. yeah, it would turn to true, and then we convert it to float. If we had 1, it's 1.0, and that item, it just to extract the Python number from the tensor, which usually gives us the final index. It's 0 or 1. So yeah, we run this one. Yeah, so it classified this image as fake. Now we would test it on a real image. So it was real and it predicted as real. Here it's fake. So yeah, that's the model is predicting correctly. So finally we would save the model weights and the learned parameters to a file, because so next time if we would like have an image and we want to check if it's real or fake, we can just download the file that we named DeepCNN model weights to make predictions without having to train and wasting another 49 minutes of our time. So let's run this. Oops. So after running this final cell, we finish the project, and thank you for watching.